All right, let's take a look at another question. The question is, the following phase diagram shows the part of vapor pressure curves for a pure liquid, green. So this is pure. And a solution, which is the red curve. So this is the solution of the first liquid with a second volatile liquid. So the second volatile liquid has not been shown. Okay, so what you're given is two curves. One, which is green, is for a pure liquid, and the red curve is the solution of the first liquid with the second volatile liquid. So the second volatile liquid we haven't actually shown. The question is the boiling point of the second pure liquid, the one that we have not shown, is that boiling point higher or lower than that of the first liquid? Recall, anytime both of the liquids are volatile and they do have the capability to show a vapor pressure, essentially the solution is going to be intermediary of both of those locations. That means if you were to position the second liquid, it's going to look like that. That means it's going to lie higher as compared to the solution curve. If the vapor pressure is going to be higher, if vapor pressure is higher, that would mean that the boiling point should be lower. Okay, and great examples of these liquids like ether or methanol or ethanol, which have an organic component. They are non-polar in nature, and hence those molecules are free to go from liquid phase to gas phase, and hence the vapor pressure in those cases is pretty high. On the other hand, if you consider water, since one water molecule is tethered to another water molecule through hydrogen bonding, and it's a pretty extensive three-dimensional effect, you would see a lowering of the vapor pressure in that case. All right. So before we move over to the next colligative property, I just want to go over, summarize the Raoult's law that we discussed, through another method. I want to show you kind of graphically how vapor pressure of a particular solution is going to vary with mole fraction of a particular component. So here I'm plotting A. So let's say that we have two components, A and B. And I'm going to vary one over the other. Realize that since it's a mole fraction, that means that overall chi A plus chi B can only be equal to 1, which is why we are plotting between 0 and 1. So if the amount of chi A is 0, that means it's purely B. Let's say it has some vapor pressure. And so this is the pressure of pure B. Let's write that. P0 B is what it is. And of course, when the chi A is 1, that means all that you have in that particular liquid, in that particular sample, is right over here. It's P0A. Okay, and what we are going to do is we are going to vary maybe 0.2, 0.4, 0.6, and 0.8. Okay, so realize that if chi A is 0.2, that would mean that chi B would be 1 minus 0.2, so that will automatically become 0.8 in that case. Likewise, chi B will be 0.6 here, and 0.4 for the chi A value of 0.6, and 0.2 for the chi A value of 0.8. Hopefully you can see that as we increase the concentration of, or the amount of A, so as we go in this direction, essentially we will measure some vapor pressures, right? And so they would be, let's just, for the sake of argument, maybe here. And now if you have to draw graphically what your curve will look like, your curve will look like a straight line. Mine didn't come out as well as I expected it to. It'll come out to be a straight line if and only if this is an ideal solution. And recall, ideal solutions were dilute solutions, right? Likewise, if you try to vary and try to measure out the vapor pressure of the system for each of the components, and now you keep the B in mind, essentially you would have a curve which will look like a straight line, which will go from the origin to that part. So if this part measures the partial pressure due to component B, and this part measures the partial pressure due to component A, then the vapor pressure of that entire solution, which is a combination of A and B, will be given by the line that I just drew. Maybe let's color code that. So the vapor pressure of solutions as the chi A is varied, that's given by the line up top. Now, in reality, however, you will not see these as straight lines. In reality, the lines could be curved like that. This line could be curved, and consequently the vapor pressure would be curved as well. So it's not like a perfect straight line, but rather curvy lines. And those are what are called as deviations from Raoult's law. These occur when the curve is below the straight line. Essentially what that means is that we have strong solute-solvent interactions. Because if the solute-solvent interactions are strong, then the solute tends to prevent the solvent from vaporizing readily. And so if the solution is sufficiently dilute, then the effect will be small, and then Raoult's law will work to the approximation. If the solution is not dilute, then this is going to be significant effect, and consequently the vapor pressure will always be lesser than predicted by Raoult's law. So your numbers will always be lesser, and the curve will be under what you expect. On the other hand, if you have weak solute-solvent interactions, then you're not going to see this. You're going to see the opposite of that. Let me erase these curves, the blue curves. If your interactions are weaker between the solute and solvent, then you're going to see, I'm going to use the dashed red line, you're going to see a curve higher than what the Raoult's law predicts, because solute and solvent are not interacting with each other, so there's no way that they can bind each other, and that is the reason your solvent would be able to make it to the vapor phase, and you will see larger readings than what you expect. Let's perhaps apply a concept problem and see if we actually understand this. Let's say the question is, a solution contains equal amounts, so equal moles of A and B. There are two liquid components, okay? The vapor pressure of pure A, so P naught A, is equal to 100 millimeter mercury. P naught B is supposed to be 200 millimeter mercury. Okay, the experimentally measured vapor pressure of the solution, so P solution is equal to 120 millimeter mercury. And the question is, what can you say about the relative strengths of the solute-solvent and solvent-solvent interactions? So which one is the strongest one? Okay, that's what the question is asking. Realize, going back to the curve that I was trying to show you earlier, realize if you have taken equal moles of A and B, that means you're kind of looking at chi A of 0.5. right? Because if you go from 0 to 1, equal moles means that you should be right at the midpoint. Now PA is somewhere 100, PB is somewhere here. And that's what your curve will look like, going back to the curve that we were discussing. And you expect this number that at this particular case, when you have equal moles of A and B, then essentially your value should be exactly right in the middle. So you expect the value, according to Raoult's law, to be 150 millimeter mercury. But the measured value has been shown to be 120 millimeter mercury. That means that number is lesser as compared to the expected value. So your curve will look like that. What does that tell you? That should tell you, hopefully, that the solute-solvent interactions must be stronger than the solute-solute and the solvent-solvent interactions, and hence the stronger interactions have lowered the vapor pressure from the expected ideal value of 150 millimeter mercury. Let's continue this discussion of vapor pressure and extend it to the other colligative properties for freezing point depression and boiling point elevation. I want you to think about the phase diagram that we discussed in the previous chapter, in which we were basically plotting pressure versus temperature, right? Vapor pressure and temperature was what we were plotting. So if you have a pure solvent, you can perhaps envision the generic shape of a phase diagram kind of looks like that, where this is where you have the solid, this is where you have the liquid, this is where you have your gas. Let's say this is your point O, where all the three meet, and we are going to call that the triple point. Remember that? And so at any given point of time, let's say the external pressure is 1 atm. The 0 to A curve is going to measure out the normal melting points. On the other hand, and I'm saying that it's normal because that's the 1 atm pressure. If you extend that to the 0 to B curve, that's going to measure the normal boiling point, right? This was normal melting point. And if you wanted to actually read the temperature values, you can read that from the temperature curve on the x-axis. We've discussed that. Now, turns out, so this is for a pure solvent, right? This is for a pure solvent. Turns out, when you put a non-volatile solute in there, recall from our discussion on vapor pressure lowering, that since now you don't have as many particles which are on the surface, which are ready to get converted into the vapor phase, the vapor pressure is going to be lower. So if the vapor pressure is going to be lower, what must be done? You must supply additional energy to the system so that more and more molecules get converted and get into the vapor phase. So only when you heat this up, for example, only when you supply energy, you would be able to get to a point where now you have more vapors or more molecules in the vapor phase, and hence you can say that that additional energy is required, or lowering in vapor pressure has occurred. It turns out that this vapor pressure lowering occurs at all temperatures, and you can see the effect by, if you were to plot, let's say, a solution, since it's a lowering of vapor pressure, the curve is going to look like that, and the curve here is going to look like, so you're going to see lower values of the vapor pressure at any given point of time. And how does that culminate in boiling point? Like I said, you will have to supply additional energy to get the same value of vapor pressure as you had in case of a pure solvent. Well, let's see in the curve what it means. Let's say your water usually boils at 1 atmosphere is the external pressure, and let's say that boils at 100 degrees Celsius. Now, if you have put a little bit of sodium chloride in it, then it's going to cause lowering of vapor pressure. So now, in order to get the same external vapor pressure, you will have to extrapolate onto the red curve. Of course, I don't have a ruler, but this really should be a straight line. Notice it's going to occur at a higher temperature. So don't you think that the boiling point has increased now? And if you were to add more and more non-volatile solute, the lowering of the vapor pressure is going to be further down. So let's say you added another lot of the non-volatile solute, then the vapor pressure would be further down, and that would mean that the boiling point would be further elevated. So essentially one can say that the difference in the two boiling points is going to be a measure of the amount of the non-volatile solute that you have added. Let's take a quick look at how the melting point differs. So notice while boiling point elevates, the melting point is the curve OA. So as we have increased the amount of non-volatile solute, the freezing point depresses further down. So it moves to the left-hand side, and hence we say, if you were to read that, we say that it's going to show a decrease in or a depression in the melting point, which kind of brings back to the idea that we were discussing earlier in the last screencast, where I said that we add salt to prevent the water from freezing at 32. So you're depressing the freezing point further down, and hence you're able to prevent accidents, really. I also gave you the example of an ice cream maker. Because you're able to depress the freezing point, the cream at that temperature freezes, and there you go, you have your ice cream that gets generated. So this is the better looking curve, but I also wanted to show you, kind of hands-on what happens. But you can see here that the pure solvent, those vapor pressures are higher than the vapor pressures for the solution, and this effect is seen over a range of temperatures. Notice it's throughout the curve that we are seeing this. And notice that the vapor pressure for the solution is shifted downwards. It's shifted downwards compared to that of the pure solvent. And so since the vapor pressure curve intersects the solid gas curve at a lower temperature, the net effect is that the solution will have a lower melting point, and for the reasons I discussed in the previous slide, it will have a higher boiling point. These are what we refer to as the freezing point depression and the boiling point elevation, and both of those are colligative properties, and I just proved that to you in the previous slide again, that as you increase the amount as you increase the amount of the non-volatile solute, the extent of depression and the extent of elevation is also going to change. Your lab is going to be based on exactly this idea. What you would be doing is essentially between you and your lab partner, you would be assigned an unknown. and you have to carry out this freezing point depression experiment and be able to determine the molecular mass of this unknown solid that you have been given. So what you would do in that case is you would weigh out a specific amount. Let's say you have maybe 100 milligrams is what you weigh. So 100 milligrams is what you weigh for a given amount of the solvent. So you know the grams of solvent that you're working with, and you're going to add that amount in your pure solvent. Of course, you are going to get the temperatures for the pure solvent, and then you're going to add this amount of the unknown. So hopefully you can see that it's going to cause a depression in the freezing point. And then you're going to add another lot of 100 milligrams. So 100 plus 100 actually becomes 200. So you have just increased the molality of the system, the concentration of the system. And so hopefully you can see that if in the first case, let's say it depressed by some amount, in the second case, in the second edition, it's going to depress further down if you were measuring temperature versus time. And that's what the lab is about. So you would be able to essentially plot and carry out, figure out for yourself where the difference in the depression in the freezing point from the curves. You would be able to determine that from the curves and be able to plug that value in, because this depression is directly proportional to the molality of the system. So this depression, the delta TF, is proportional to molality of the system. When you remove the sign of proportionality, you have to introduce the constant of proportionality, which is Kf, and that's a known number. It's a constant. The delta Tf is an experimental number that's coming from the curve, and molality, recall, that was the moles of solute divided by kilograms of solvent. Kilograms of solvent. The kilograms of solvent is an experimentally determined number, so you actually have that. You're the one who measured it. You have that number. Molality is all that we have to figure out, or I'm sorry, the number of moles is what we have to figure out, since the number of moles is mass over molar mass. Once you have figured the number of moles, once you know the mass, because you're the one who measured whether it was 100 milligrams or 200 milligrams, don't you think you would be able to calculate the molar mass? So it's pretty simple math that we would be incorporating. It just is stepwise, and when the time comes next week, I'll be discussing this in a little bit more detail, but I wanted to give you an idea of what to expect in that lab. This slide basically provides, what's what in the previous curve. Since we already took the time to discuss that, I'm going to go forward with it. But I definitely want to say that the freezing point, what I was discussing a couple minutes ago, the freezing point of the solution containing the non-volatile solute is lower than the freezing point of the pure solvent. And so for example, the antifreeze that you use, to prevent the engine blocks in cold climates, that's an aqueous solution of ethylene glycol, the structure of which is this. This is a CH2. This is also a CH2. And so the more concentrated the solution, lower the freezing point becomes. So this is present in your radiator, and just an FYI, while we are at it, this is a sweet tasting liquid, and is poisonous. So we should not keep it in keep it in your garage at lower levels where children or pets can actually get to it pretty quickly. So anyway, let's discuss Let's discuss the elevation and boiling point and the depression and freezing point a little bit more. As I was saying, that the delta TF is dependent on the amount of the moles that you have added, specifically as a molality. One can say that delta TF is going to be equal to Kf times the molality. So now, since molality is moles per kilogram of the solvent, delta TF is experimental, Kf is a constant, kilogram is an experimental, moles is mass over molar mass. You can determine the molar mass of an unknown material. Maybe we'll do 1 or 2 problems based off of that as well. But realize delta TF is the change in temperature in freezing point in degrees Celsius, and even though it's a depression, it's reported as a positive number, so you can consider that we are going to use the absolute value. Of course, M is the molality and Kf is the freezing point depression constant for that solvent. For water, just a reference point here, for water that value is 1.86 degrees Celsius per mole. Likewise, if you're considering Kb, you can simply say that delta Tb, the change in the elevation and boiling point, that is also proportional to the molality. And what that means is when you remove the sign of proportionality, you have to introduce the constant of proportionality. Again, the same way as delta Tf, the Tb will be an experimentally determined number. Kb is a known constant depending on the system that you have. That value will be given to you. M is the molality, which is the moles per kilogram of solvent again. And so you should be able to determine the molar mass of a given unknown if required. All right. Now, a lot of times people think that if you have an aqueous solution that contains some, solid solute and it freezes slowly because there is depression of the freezing point, the ice that gets formed basically contains the salt also, and that's not true. It does not normally contain much of that solute at all, and just to give you a reference point, when you're thinking about the ice that forms in ocean water, for example, the ice is not salt water, it's actually fresh water. As the ice forms, the crystal structure of the ice tends to exclude the solute particles. You can even try this, in your refrigerator, or if you try to take that ice and you try to melt it, you would be able to drink it. It's not seawater at all, so it would be much less salty. Okay, let's try to solve a question. The question is, what is the normal boiling point in degrees Celsius of a solution prepared by dissolving 1.5 grams of aspirin in 75 grams of chloroform? The normal boiling point of chloroform is 61.7 degrees. The Kb for chloroform is 3.63 degrees Celsius kilogram per mole. All right. So several things. We are looking for boiling point. Recall, just for the sake of reference, I'm going to say, let's say this was for chloroform by depression. You would see that it's going to be elevation in boiling point. So we are expecting that if the normal boiling point of chloroform was 61.7, this new boiling point for the solution is going to be slightly higher. We just have to say how high, okay? Now, the delta Tb is equal to Kb times the molality. If we are able to calculate this elevation, we can simply add that to the basic value of the boiling point of pure chloroform, and that will be the elevation of the new boiling point. The Kb value is given to be 3.63 degrees Celsius kilogram per mole. We are given molality, So that would be the moles of solute. So I'm going to say 1.5 grams divided by, let's determine the molar mass of aspirin. So that will be 9 times 12 plus 8 times 1 plus 4 times 16. That should come out to be 108 plus 64 plus 8. So that is 72. And this should come out to be 180, is what I'm getting, grams per mole. So I would say that the moles are 1.5 grams divided by 180 grams per mole. Grams and grams will cancel off, and moles and moles will also cancel off. I'm supposed to write down the solvent, which is chloroform, in kilograms. Since I have 75 grams only, I can divide that number by 1000, and that will give me a value 0.075 kilograms. The kilograms and kilograms will also cancel off, and looks like my delta TB, which is the change in temperature, is going to after all come out in degrees Celsius. So the math here running is pretty simple. 3.63 times 1.5 divided by 180 whole divided by 0.075, and you're figuring that out. So this part for me came out to be 0.0083, and I'm going to divide that number by 0.075. That's 0.11. So 3.63 times 0.111, 3.63, and that gives you the change by 0.403 degrees Celsius. And so that means that the new boiling point is going to be, so new boiling point meaning the final, that's the TB solution minus TB solvent, is 0.403. If this value was 61.7, you must add 61.7 to the new number that you got, and that will give you the TB solution to be equal to 62.103 degrees Celsius. Okay, sound good? All right, let's go forward. Okay, I want to try out another question so you can kind of see where we are going with this. The question is, what mass of ethylene glycol in grams must be added to 1 kilogram of water to produce a solution that boils at 105? So you're given that your solution is supposed to boil the, let's write it differently. So you're, or maybe write it with blue. So TB solution is 105, and you know that TB solvent for water, we know that it boils at 100 degrees Celsius. So we know that the change, the delta TB, is going to be worth 5 degrees, right? Now we have 1 kilogram of water, 1 kilogram of water, right? So I can say delta TB is equal to KB times the molality. Of course, I will need the value of KB, and that's a number you can get from, a table in your book. In a test, of course, that value will be provided to you. For the case of water, that value is 0.513 degrees Celsius per molal. And we have defined the molality as moles of solute divided by kilogram of solvent, which, by the way, is 1 kilogram. That's the value that we have been provided. So we can say that the 5 degrees that we are getting is equal to 0.513 times the moles of ethylene glycol that we have, right, of glycol. And you know that moles are nothing but mass divided by molar mass. So if you knew the molar mass, you would be able to simply calculate the mass that is required to bring out this kind of a change. How do you determine molar mass? You have been given the formula, so simply calculate the molar mass based on the formula. That is 2 times 12 plus 6 times 1 plus 2 times 16. So that will come out to be 24 plus 6 plus 32. I'm getting a value of 62 grams per mole. So I'm going to plug that value in over here. And when you solve for mass that you require, you would say it's 5 times 62 divided by 0.513. That value comes out to be 604. I have no room to write. Let's erase maybe parts of it, since you've already seen. Come on. And this number comes out to be 604.2 grams. And that is your final answer. Okay, the last colligative property is on osmosis and osmotic pressure. So let's first discuss what osmosis is. Osmosis can be defined as the flow of solvent from a solution of lower solute concentration to one of higher solute concentration. Well, what do we mean by that? I want you to first think about what happens when you take water and you perhaps drop, like a drop of food color or ink in a glass of water. What do you expect to happen? That's what I want you to envision. So you took a beaker. Let's draw that. You took a beaker and it contains water, and you have just dropped. Hopefully you can envision that as it touches water, so slowly over a period of time, the entire water would take up the color of that food color or ink, whatever it is that you had added. In this case, it's the solute particles of that ink which have dispersed through the bulk of the solvent. We call this process diffusion. Okay? We say that this is diffusion of solute particles. Osmosis is kind of the opposite of this. It's the movement of solvent particles, not solute, but solvent particles, and that movement has to occur across a membrane, across a semi-permeable membrane. The reason why we are using semi-permeable membranes is because they will allow the passage of smaller molecules like water or a solvent, but they will block the passage of larger solute molecules or ions. Okay? So if you have a solution and a pure solvent which are separated with the right size of the semi-permeable membrane, only the solvent molecules are going to pass from the region of lower concentration of solute to a region of higher concentration, because of course there is a gradient, and so we use the word osmosis to define this process. Now, till what time does this passage keep on going? This keeps on going till the time that equilibrium has been established. Let's perhaps view, I think I have a picture on the others in a couple of slides. Yeah. So what you're seeing in this picture is essentially you have a container which has salt, and then there's a inverted thistle funnel which contains a liquid, and then there is a membrane. The membrane is right here. This is the membrane. The membrane is going to only allow the passage of your solvent molecules. So solute particles cannot come out of there, rather solvent can get in. So what do you envision? the region outside was lower in concentration with respect to solute. The region inside has higher concentration solute. Because of this difference in concentration, essentially water is going to gush in, and over a period of time, the level of water is going to increase, which is what you have. And so if you started with, let's say, 1 molar concentration inside, which is kind of shown by a darker green, notice over a period of time, what becomes the concentration, or at the end of the day after the experiment, is less concentrated for that reason, because now you have added more solvent molecules in that system. And this difference, this gradient, is what is referred to as the osmotic pressure. All right, so osmotic pressure is essentially the pressure that is required to stop the osmotic flow at any given point of time. So like I was saying, that this process of movement of solvent particles from the outer region inside that funnel is going to continue by osmosis from the pure water side into the salt water or sugar solution, whatever it is that you have taken. It is going to continue to happen till the time that equilibrium has been reached. And so if an external pressure is applied to the water, then the process can be stopped, and the pressure can be measured as molarity. It's given as pi. It's given as a product of molarity times R times the temperature. It actually partially is derived from the PV equals nRT. Since pressure is nRT over V, N is number of moles over volume, which by the way is molarity. So it's similar to that in that aspect, but the pressure we are talking about is osmotic pressure in this case. Okay, now like I said, pi is how we denote that. M, capital M, is the molarity. Gas constant has a specific value. The number will be given to you, 0.08206 liter times atmosphere per mole per Kelvin, and T is the temperature in kelvins. The question is, what osmotic pressure in atmosphere would you expect a solution of 0.125 molar, so this number is 0.125, that is separated from pure water by a semi-permeable membrane? The moment you see semi-permeable membrane, think osmosis. So temperature is 310 Kelvin. R is a gas constant, 0.08206 liter times atmosphere per mole per Kelvin. So the Kelvin and Kelvin will cancel. Molarity is moles per liter, so the moles and liter will cancel. Your final answer will come out to be in atmospheres. So let's get the product of the three numbers that we have. So on my calculator, I'm punching in 0.125 times 0.08206 times 310. And I got a value of 3.17 atmospheres. And I'm going to report it as 3.17, not 3.2, because my given data has three significant figures. So I have to stick to that. Okay. Let's go forward. Realize what we have done so far. We've talked about four properties, and all of these could be used because they either employ a mole fraction, they either employ molality, or they employ molarity. And so all of them do have the concept of moles within them. So you can actually, theoretically, you can use any of these to determine the identity of an unknown material, and you can use that to determine the molar mass of the unknown substance. But of all these, osmotic pressure usually gives the best results, and that's what is used in most delicate biological systems as well. Let's see if we can apply that to a situation here. The question is, what is the molar mass of sucrose if a solution prepared by dissolving 0.822 grams of sucrose in water and diluting to a volume of 300 milliliters, has an osmotic pressure of 149 millimeter mercury at 298 Kelvin. So we know that pi is equal to capital M RT. Realize you can only use the value of R of 0.08206 liter ATM per mole per Kelvin. You can do that if the osmotic pressure is also in atmospheres. So in order to convert the 149 millimeter mercury to atmosphere, you have to divide it by 760, since 1 ATM is 760 millimeter mercury. So you can say, let's just write it again. So you can say 149 millimeter mercury times 1 ATM, 760 millimeter mercury, millimeter cancels off, and you get your answer for the osmotic pressure. R is a constant value, temperature is 298 Kelvin, molarity is moles of the sucrose, so that will be 0.822 grams divided by the molar mass is my unknown that I'm seeking. Volume is 300 milliliters, but realize in molarity we always write it in liters, so that number is 0.3000. So now we just plug in the numbers, do our calculation. So on your left hand side you have 149 divided by 760, and you can calculate it if you want to, if that makes life easy for you. You can go ahead, do that, or you can consolidate everything and then just determine the molar mass, however you want to do it. It really is your level of comfort with, math. 0.08206 times 298, and so let's punch in our numbers. My left hand side, I'm going to show you the breakup anyways as to what each of those numbers should come out to be. So this part should come out to be 0.196, and this part should come out to be 0.6 times 298 times 0.822 divided by 0.3 divided by the molar mass. Whoops, molar mass. And so cross multiply. So when you would divide the 67.003 by 0.196, the molar mass comes out to be 341.8 grams per mole. So again, you can do it stepwise, or you can consolidate however you want to do it, but I wanted to show you how to plug in the numbers. What I want to do right now is give you the formula of sucrose so you can make sure that the answer that you got, you may not be able to do that in a test, of course, but in this case we can do that. So sucrose is C12H22O11. So 12 times 12, that's 144. 22 times 1, that will be 22. 11 times 16, that will be 176. And I'm going to add those and see if I actually get a number similar to the 341.8 that we got. And I'm getting, it all adds up to 342 grams per mole. We're good.